So today we discuss refraction and reflection of a plane wave using Huygens principle, and previous class we discussed see here refraction of a plane wave using Huygens principle. Here we discuss refraction and light travel from rarer medium to denser medium, and today discuss light travel from denser medium to rarer medium. So jump to the whiteboard, discuss light travel from light travel. Actually the wavefront, okay, here we discuss the wavefront. Wave travel from denser to rarer medium, okay, with the help of Huygens principle. Okay, so here see the diagram. Upper medium is a denser medium, okay, this is a denser medium, and this is a rarer medium, and so light, actually the wave here, wave and this wave, okay, that's the incident wavefront. Actually the incident wavefront look like this. So draw a perpendicular from this line to this line to from, okay, to from this line we get a 90 degree, and this is a incident wavefront, then wavefront, okay. And so light travel from denser to rarer medium, so there is a normal to normal here, okay. And now the bending, so the bending is the refracted bends away from normal, so look like this, away from normal, okay. So now draw a perpendicular from this point to this line, just look like this, okay. That's a refracted wavefront, refracted wavefront, okay. So now see that this angle I, okay, incident angle, there's a refracted angle R, and here the name of the point, this point we suppose A, B, C and D point, okay. So here see that conclusion, light travel from denser to rarer medium. So speed of the light from denser medium, suppose V1, and rarer medium is V2. So V1 is less than V2. V2 is higher than V1 because there is a V2 is the rarer medium, and we know that light travel faster than denser medium. In rarer medium, light travel faster than denser medium. Okay, that's why V2 is greater than V1 or V1 is less than V2. Okay, so light travel from denser to rarer medium. So light travel from denser to rarer medium. Okay, that's the refracted wavefront, and that this length, okay, and you see that this length, okay, that's the BC, so that is equal to V1 times tau, this length, I can displace here, and this length AD, this length, that's the V2 times tau, V2 times tau, that's the displace, okay. So when a light travels from denser to rarer medium, so you know that the velocity of medium 2 is greater than medium 1, so that incident angle I is lesser than refracted angle. So that when light travels from denser to rarer medium, so when light travel from denser to rarer medium, denser to rarer medium. So the I incident angle is obviously lesser than refracted angle because refracted angle is more. So now if the refracted angle is more than incident angle, so that hold for Snell's law, that's a valid or hold for Snell's law, that is n1 sin I, that is equal to n2 sin R. Okay, so sin I by sin R, that is equal to n2 by n1. Okay, and now see that this diagram. Okay, and here the light travel denser to rarer if so here is some condition if R refracted angle is equal to 90 degree. So if R is equal to 90 degree, so copy the diagram. So here if R is 90 degree, okay, so R 90 degree means, so light, if I say that is there is a denser medium, that's a rarer medium, so that is a incident ray, and if R 90 degree means there is a normal and there is a refracted ray, that's a refracted ray here, so that's why this angle will be 90 degree. If R equal to 90 degree, okay, so that is diagram look like this. There is a wave front and these other things. So similar both case R is 90 degree, so we get sin I by sin R, sin 90 degree, that is n2 by n1. So if sin 90 be the 1, oh, so actually sin 90 be the 1, obviously sin 0 0. So sin I equal to n2 by n1, and that incident angle, this I is called critical angle. Okay, that's angle I is a critical angle. So this angle is called IC or called critical angle IC, and now this I turn into IC. Obviously this is an incident angle. So now this angle, another name of the incident angle is called critical angle if refracted angle is a 90 degree. So there is another concept here, that's a critical angle. If incident angle is another condition is a incident angle I is greater than critical angle. So if incident angle is greater than critical angle, now same condition here, this refracted ray back to the denser medium, then that refracted ray back to the denser medium. So that's the incident wavefront, that's the incident wavefront, and now there's that refracted wavefront. Wavefront back to denser medium. Now this refracted now is called, is an actually they are back to same medium, so that's why it's a reflection. This is called, here is a reflection. We know that if the incident ray back to the same medium, okay, that's called reflected ray. So that's why this is called total internal reflection. When I refracted ray back to the same denser medium, so that is why this refracted is called incident ray. Now this phenomena is called total internal reflection. There is a no refraction. So here is no refraction. Okay, clear? So now this is the concept here. These are the wavefront. Wavefront also satisfy that laws of reflection and laws of diffraction, and also the critical angle and also the total internal reflection. Clear? These are valid for both. Okay. Now we discuss reflection. That's the reflection. reflection of a plane wave by plane surface. So here plane surface. Okay, here we discuss refraction, okay, from denser to rarer medium, and before that we discuss light travel from this is refraction. Here light travel from rarer medium to denser medium. That's a two refraction. That's a two part. Light travel from denser medium to rarer medium, or rarer medium to denser medium. But here reflection, there is no refraction, so there is no medium here. Actually the medium concept not valid for here, not needed. So there is a plane surface, okay, and I say that it is a m, and say that is a m dash, the plane surface, and that suppose these two are incident wave front. When I draw this line, this 90 degree, okay, perpendicular of this line from this point, okay, that these are incident wave front, okay. Now after strike this ray back here, and now draw a normal here. These are the normal, so that's angle bi, incident angle I, okay, clear. Now if I draw another point, so now with the point name, suppose the point A, that is the point B, and that point is say that C, and that velocity of this medium, suppose a v1, the velocity is v1, so that's length is bc, that is equal to v1 tau, or suppose 1 medium, that's why it's a v1 tau, and okay, and this length, okay, bc cut from a to suppose a d, okay, ad, and this ad also, that is a v1 tau, this length, because the AD and BC be the same. I choose that CB, measure the length of CB and cut AD. Now I draw a sphere from sphere of radius V1 tau. Okay, this green color sphere, radius of green color sphere is V1 tau. Okay, now draw a tangent from D. Now draw a tangent from D passing through the C. You will look a tangent passing through the C. That's a look like a tangent. Okay, don't be confused. These are look like a tangent from point a tangent, that's a sphere, or say that is a two-dimensional circle, and passing through the point C. So now we know that that is a radius v1 tau, and there is a tangent. Tangent and radius, they are mutually perpendicular from geometry class, I think class 9 or 10 geometry, from circle chapter. Okay, we know that that is a perpendicular, radius is a perpendicular to tangent, or tangent is also perpendicular to radius, vice versa. Okay, that's the incident wave front, and these are, if I strike back to the, suppose is the same this length, okay, and this CD, and this CD is called reflected wavefront, reflected wavefront. Okay, and now so the AD, that is equal to BC or CB. So here we prove the Snell's law from this diagram. So here you see that the two triangle here, triangle ADC, triangle ADC, and triangle ABC. Okay, and this angle from this angle be that I, okay, and this angle be the R, And if I draw a perpendicular here, normal, actually these are the normal, so this angle refracted R, so this angle theta also R. So that is two triangle ADC, a triangle ABC. Okay, now we prove the congruency of these two triangles. Now we prove that AD that is equal to CB. Okay, actually the length be the same, AD and BC. Okay, now another AC common side. AC is the common side between these two triangles. Okay, and now ADC and ABC are 90 degrees. ADC and ABC are 90 degrees. So triangle ADC congruent triangle ABC from side angle side. Now after proving the congruency, we said that that is a DCA from triangle ADC that is equal to from triangle ABC that is BAC. Okay, from CPCP corresponding part of congruent triangle that is equal to I equal to R. Now we have the laws of reflection. Okay, there is the derivation for laws of reflection. Okay, so here also they are valid with the help of Huygens principles. Then we discuss three parts here: the refraction of a plane wave, a thin lens, convex lens, and concave lens. So here just we draw a diagram. Now we draw three diagram. Okay, the first diagram is a refraction of a plane wave, a thin prism. Okay, so now we discuss that some refraction part here. Just we draw a diagram. Okay, the very easy diagram. That's refraction. Actually, using the Huygens principles, refraction of a plane wave, a thin prism. Okay, so that's a thin prism. So now these two are incident wavefront. These two are incident wavefront. Yeah. So after striking that, actually light travels from rarer to denser. Now here that's the refraction. So now draw this line here. Okay, so that's if actually this line, these two are perpendicular. Okay, perpendicular. These two are perpendicular. Okay, there's a refracted wavefront. Now second we draw another diagram, refraction of a plane wave, a convex lens. Same as refraction of a convex lens. So now that convex lens. Okay, so okay, these if I draw that's the incident wavefront, incident wavefront. Okay, so now after striking, that is refracted ray is converge and meet focus F. Okay, so we get here a spherical wavefront of radius A. So that's the focal length. This is the focal length, and we get spherical wavefront, spherical wavefront, okay, of radius, focal length. That's the focal length. Okay. So here we get a spherical wavefront. Now, if I change this lens, is a concave lens. So now the diagram is look like this. Okay. So now that's obviously incident wavefront. So this is a incident wavefront. Okay, and so after striking, they refracted it diverged. So if I back to that medium, so now we get F point here, and get a also we get a spherical wavefront. Also, you get a spherical wavefront. Is now okay. And we get a spherical wavefront. Spherical wavefront of radius, focal length, or r by 2, radius of curvature by 2. Okay, actually back to here. So here the conclusion is that when you choose a convex lens, so the actually spherical wavefront in opposite side behind the lens, and when you choose a concave lens, so spherical wavefront we get also spherical wavefront. Okay, radius will also be the same, both are be the same, but in same incident form. Okay, when the same incident wavefront, okay, same side, and that's the behind the lens, that's the front of lens. For concave, there is a front of lens, spherical wavefront create a front of lens. Here create a spherical wavefront behind the lens or back of the lens. Okay. So that's the basic discussion. Okay. So next class we discuss the coherent and incoherent addition of the wave. So today in the class here, if you have any doubt, please ask in comment section. I will try to give the answer. Okay. So thank you for your time.